model. Then you try to schedule these the graph into a real system, right? So what we try to do is to look at this, like first look at the kind of theoretical model. Right? And remember, we have 3 stage, right? So it's like a pipeline. So we know the pipeline, assemble car pipeline, you have different stage, right? Doing different work at a different stage. So in our case, it's like a 3 stage. You do local, right? Local IoT device, or then the communication, then finally the remote. So that's why we have this LCR. Right? Then just imagine that each circle means that a job, like a box of a DNM. Right? So this number, like a 422, means that if you do local, the computation time will be 4. But if we do this communication, right, then it's a 2. And then another 2 means that if you do remote. So you just give a choice. You can either do it local, or you send the data to communication, right? Then either you can send this, also conduct everything in the remote. So let's just look at example. Suppose we have a cut. Cut really means this is the place that you do the offloading. So that means the first 4 units you do local, then you have a communication. The communication cost for this one is 1. Communication cost for this one is 4, right? This is number 4. Then the remaining one is just remote. So you're doing basically like a pipeline. So the first 3 with 2, 3, 4, right? You do a pipeline. Suppose you do 3 first, then 2 and 4. After you complete this stage, then you have a communication stage, right? 4 to 6, 3 to 5, right? So that's how we look at the duration for this communication. Depends on this value, right? It's 4 and 1, so that's why. After that, we do it the remote. So if we do this kind of schedule, then a total duration is 15. But can we do better? The answer is yes. So let's just look at this example. Suppose we schedule 2 first, 4 and 3. Before this 3 completed, actually you can start the communication after 4, right? So that means if this is done, then you can start communication. So that's the idea of this pipeline, right? You don't have to wait until the first stage is complete. So that's why you can see the S4, which is communication, can start right after 4 is completed. And the same thing is like when 3 completed communication, then the last one is the 5, which is a remote, right? So now you can see that the time is saved, right? Saved for 2 units. So it's 13. But can we do even better? Yes. Then you have to be very careful, like schedule this, the first stage, right? This first stage 2, 4, 3. You can start with a 3, 2, 4. So that means this is start first. When this start first, when this complete, you can start communication. It's a long communication, right? So you can see that, so you can start communication early. Then the whole completion time is 9. You see this one? So in this case, it's much better, right? So doing this schedule. So my talk will focus on how you do a partition. First of all, there are 2 issues. How you partition this, this computation. So this partition point is important. Means that before the partition is local, then communication, then the cloud or edge. And even after this partition, the scheduling is not easy. Right? You can see the order becomes so important. We have 3 different orders, you come up with a different result. So what we try to first show that, unfortunately, this problem is a hard problem. We look at the different structure, right? So we have linear structure, multipath, and DAG. For linear structures, it's easy. Right? Actually, we assume that the cut is already done. Later, we'll talk about what happens if the cut is not decided. Even for the cut is done, obviously linear is simple because there's only one linear line. But multipath is already hard. And our first theorem is this multipath is NP hard, right? Even after the cut. Because this one, it becomes a problem, like classic problem is called the flow chart. 3-machine or 3-stage flow chart problem. It's a famous NPR problem. Okay? Now what we're going to do, Right. So this is, we go back to the first page when I mentioned that if you're facing some difficult problem, can you come up some easy one and solve it? So that's we try to do. So what we try to start to do is that obviously for linear we can solve, for multipath, how we handle that? So we look at one of the classic, very old result called extended Johnson algorithm. So this algorithm, I show this one. Again, assume that you have a multipath. So what mean multipath? Let's just look at the example, right? Like this one, you have a two paths. The upward, there's one path, then downward, there's another path. But each path is three stages. Stage of local, communication, then remote. So what you can see that, suppose I give you like three paths or four paths, like in the box, four paths. Then the computation time for the local is 3, communication is 2, then remote is 5. So for each path, you have a different time. Now the question is how you schedule those, right? The order becomes very important. So this one just show you one order, it turned out to be the optimal. The order means that you first just do 1, 3, 4, 2. So the challenge is how you decide this kind of order. So once this order is done, then you do the pipeline. Pipeline means that once first stage local complete, then your communication, then the remote, right? So you just do this pipeline. So how you determine the order? The order is determined in this way, based on this algorithm. We just look at this 2 column, right? 3 column. So this column local, communication, then remote. We look at the first 2 column. You add these 2 together, 1 plus 2. Right? They compare with 2 plus 3. So basically you compare this 1 and 3. And if you find that the 1 is smaller or equal than 3, then we say that this task or this path belong to H. Right? So we classify the paths into 2 groups. One is called H group, the other one is L group. So by this, we can easily see that H group, you have only one path, which is 1. 2, 3, 4 belong to L because the first local is larger than the remote, right? Then we'll sort this order. This order is very important. The H should be the increasing order based on the 1 and 2. Since there's only one task, you don't need to sort. But for L, there's a three paths, right? So you sort based on the decreasing order of 2 and 3. So you can see that 2 and 3, this is 4, 6, and 5. So the decreasing order should start with a 3, right? Which is 6, then 4, then 2. So this order becomes so important, right? Then you just put H first, then L. So it should be 1, 3, 4, 2. So this is where 1, 3, 4, 2. And if we follow this kind of algorithm, partition, and you get a good result. So why this is a good result? Obviously, since this schedule is an NP-hard problem, you don't get the best result for all the cases. But for special case, you can get the optimal result. So what's the optimal result? The optimal result is that it happens when you look at the minimum of local. What's the minimum of local? In this case, it's 3. Then the minimum of a remote. What's this one? It's 2. Then you pick the maximum of these 2. So 3, 2, then get a 3, right? Then this is called the maximum of a minimum. Compare with the maximum of the communication. In this case, is a 3. So you can see that 3 equals to 3. So this condition is satisfied. If this condition is satisfied, then this extend Johnson algorithm is optimal. So that means some special case, if we follow this rule, we get the optimal result. And what happens if this condition is not satisfied? Then you can prove that there's a so-called approximation ratio. So this is actually a relatively old result, but it's very useful. It means that you can schedule those kind of multi-paths and get quite a good guaranteed performance. Okay, so this is our first, I can use some of the old result. And we apply this one to a real like a test bed using local is the phone, right, or Raspberry for our local computation. Then we use either 3G, 4G, or Wi-Fi for communication. So it depends on the speed of communications, we have a different result. And for the cloud computation, we use Amazon EC2. Then when we, obviously we compare with some other scheduling method, local only, and this is our extend Johnson algorithm with this color, blue color, and there's other ones. I'm not going to go through this. But you can see that for all the cases, and this extend Johnson can beat all the other cases. So that means it's a relative good performance, and it's very easy to schedule. Although this is an NPR problem, but you can use this kind of approximation to solve it. Okay? So this is the first step. I just want to make sure that I have sufficient time, although I start like 3 minutes late. But now, what we try to do is that we solve like a simple one problem, like it's a very simple means that only multi-pass. What happens if you have a DAG? Right? So we try to make a problem a little bit more difficult. So DAG is like this kind of structure. So this is a DAG. So the DAG is a concept of kind of like a fork and join. Fork means that if you have one thread, now you expand to 2 threads. Join means that initially you have a 2 tasks and now merge into 1. So this makes things a little bit more difficult. So it's not like a parallel path. So what we can do is that we can convert this one to a parallel path through replication or duplication. In this case, you can see that whenever you have a fork and join, you duplicate or you replicate, depends on the degree of those nodes. For example, this 2, you make a 2 copy. This 4, you make a 2 copy. Now you can have this kind of parallel path. Once you have a parallel path, you use the extended Johnson algorithm. But it's not exactly the same as the previous one. The reason is that you can see that 2 appear twice and 4 appear twice. You don't have to exclude both. You only need to exclude 1. So that's why it's not exactly the exact solution for the previous one. Because due to the time limitation, I'm not going to show you some kind of a performance through simulation. But this is some of the interesting idea. You can extend it. It's kind of like approximation. Okay, another type of approximation. But I want to focus the rest of talk into a much more interesting problem, more related to practical cases. So one of the most important application is a multiple DNN. Multiple DNN means that imagine you have a smart city with all this car, right? With all those kind of sensors. Those sensors doing image analysis, right? Or doing some kind of inference, right? So that you take a picture and decide well, what's inside the picture. But you have so many sensors, so you're doing all this at the same time, right? So that means it makes things a little bit more difficult. So it's not scheduling one particular task, a deep graph. Instead, you're doing multiple. Right? So the key is a multiple. Obviously, this thing is much more difficult than the previous one. But we start with a simple one, means that we have only one line. I mean, line means that all the DNN is a linear structure, right? Like an AlexNet, linear structure. But you have multiple copy. So multiple copies. So how you schedule them? And also, we don't know where's the cut. Cut means that give you a linear processing, right? A graph. How you partition the graph? For each case, right? For each copy, you do a different partition. Partition means that one part is local, the communication, then the remote. So this one is a challenging in the sense that so we studied like a multiple linear structure. You have a multiple linear structure by a multiple copy. Each copy have a different kind of cut. So if you want to do exhaustive approach, really means that you have to look at, suppose you have n copy, and each DNN is linear, it's L level, K level, means it can cut at K different location. So that's why you have a total option is a K to the N, so it's too many, right? It's too many. And I will show you one example why this is not easy. Another question, can we do it a much better solution or like optimal solution, or close to optimal solution for this case? The answer is yes, but we'll explore some kind of special property for this particular application. So what kind of property? As I mentioned earlier, and through this, you can see this example, is that when we do this DNN, the data size becomes smaller as you go down the stage. Right? So this is very important, meaning that the amount of data for transmission becomes smaller and smaller. So you can see the trade-off. So where you can do that, if you do the offloading start from beginning, obviously there's no computation, but it's a large data set. So communication is big. So you can see that this means that the red color means the communication. The blue color means that the computation, local computation. So you can see that if we do the offloading immediately, so large data set, also communication. Or you can do it offloading after first stage, means I do little computation, right? Through the convolution or pooling, right? The data size becomes smaller. So you spend some time on the local, and also you reduce the communication. So if you do a little later, you can see that the size becomes smaller for communication, which is data, but a little bit more on the computation side. Right? But the problem is that suppose you have like a 10 copy. So where's the cut? And do you need to cut all in the same place, or some cut in the early, or some cut in the later, right? So you have like a different bar, how you do that. Before we look at the detail, there is another property. So we realize that when we do this kind of offloading, especially to the cloud, cloud EC2 is very fast. So this is a real application like Alex. We find that, oh, sorry. I think the light is off, okay. And so you can see that this one, the last stage is cloud computation is a very, very small, right? So actually we can ignore that one. So once you send it to the remote, it's basically can finish instantaneously. So we just assume that for the sake of argument, we assume this is approximate to 0. So we just focus on two-stage pipeline. Why we study two-stage? Because two-stage, you can solve it optimally. Right? That's a big difference. In three-stage, we prove this NP hard problem. But for two-stage, we can do that. So how you do this two-stage schedule, optimal schedule? It's called the Johnson algorithm. It's not the extended Johnson. Again, you just, since two-stage, you have a local and communication. Then you just look at the P1 and P2. P1 means local computation and this communication. If a computation is smaller than the communication, then we put the H group. Otherwise, you put the L group. So it's the same. Then you arrange H based on the increasing order, and then for the L is decreasing order based on the 2. Right? So let's just look at one example. So suppose you do the offloading immediately, so large data set. So if we do cut like 1 first level, this is the one. Right? So suppose you have another copy, we say you cut at the 2. Right? So this is 1. Then you cut at the 3. So you can see that suppose you say that we have a 6 copy. Each copy cut at a different place. What's the best schedule? Just to illustrate the idea, right? Suppose you have a 6 copy. So what's the best schedule for that? Suppose we already did a cut. So we just look at compare with the blue and the red one. So for the one that has a larger red one, means more communication, you put the H group. So you can see that 1, 2, 3, more red than blue. So you put that one. How you arrange the order? It says increasing order of a blue. So increasing order of blue is exactly 1, 2, 3, right? Then the next 4, 5, 6, right? Blue is more than the red, right? Then the order should be a decreasing order of red. So it's perfect. So decreasing order red is just 4, 5, 6. So this is the actual schedule should be, first you put all the H in the order 1, 2, 3. Then after that you put the L, which is 4, 5, 6. And the Johnson rule show that if we do this kind of schedule to order, and this will be the optimal, right? So this just show you one example. I obviously, so this is the one. So you do this schedule, right? And you can combine whatever. So the total make span is a minimum. So I'm not going to show the detail. Obviously, for this case, it's like a communication dominant. Dominant means that there's more communication than computation, local computation. Right? So now let's go back to our original problem. Before we do that, we'll see why this problem is so difficult. Now let's look at, suppose you have AlexNet, right? So you have a cut in one, suppose you have two cut. One cut is here. Then for this cut a little bit early, then the more communication than computation, right? Or you can wait, do a little bit more computation. So the data size becomes smaller. So overall, you see the duration overall is smaller. Right? So now the question is, you have a two copy. So what are you going to do? You can do two copy both cut at L1, or you can two copy both cut at L2, or one copy at L1, another copy at L2. So you see the complications, there's so many different choices. But then what's the optimal schedule? Suppose we do a both cut, right? Both cut at L1. So you have two copy exactly. So you do a pipeline. So this is the best one. And you will finish at the 16. Then we can look at another one. Another one is one cut at the L1, another cut at L2. The optimal schedule is this one. Right? You schedule 4 before 6, 7, not 7 before 6, 4. Then this optimal schedule 4, 6, 7, 2, right? 4, 6, computation, communication. And the total time is 13. So this is better than this one. On the other hand, if we do have two copy of L2, so 7, 2, 7, 2, the optimal schedule is like this. So you can see that for this one is a computation dominant, it's more computation, right? But this one is more communication. So you can see it's kind of very tricky, right? Even for two cases, there's so many different options. Imagine you have a multiple layer, and what's the best cut? Because each copy have different cut. So fortunately, we have some interesting result. I think we still have like 15 minutes. So what's the important observation? The observation is that for computation time, it's linear increasing. Means that if we offload a little bit later, right, so more and more computation. So it's like a linear increase. So it's still like a convex function. Another one is a communication time. Remember we doing this convolution or local pooling, the data size becomes smaller and smaller. So it's monotonically decreasing. So if you rearrange this, the real data, right, to red and the blue, and this is the layer of offloading. So you can see that for the communication, the size becomes smaller and smaller. And this makes sense because you offload later and the data size becomes smaller. Obviously, if we offload a little bit later, more local computation. Right? So you can see that one is decreasing, the other one is increasing. Right? So suppose I ask you to, okay, I give you 100 copies. So how you should cut all this 100 copy? Are you going to cut it differently, or you want to cut all the same, they put together? So it turns out the result is quite simple and it's intuitive. The best one, you can treat this one as like a continuous function, right? Continuous. The best one is the intersection. Okay? So the best one is the intersection between these two lines, which just means that if everything perfect, communication and computation all at the same units of time, right? Then you can just align all this one and this much better. Because all the other cases, either too much communication or too much local computation. Right? This is like a balance, not like computation dominate or communication dominate. So that's the main idea. And we officially proved that. But in the real scenario, it's a little bit complicated. Why is it a little bit complicated? We assume that the communication and computation can be done parallel at the same time. Is that the same time? In reality, it's not, because it's a pipeline. Pipeline means that you first do computation, then communication, computation, communication. So it's in reality, it's not that simple, right? If everything can do at the same time, then it's perfect. So our overall result is the following. I'm not going to show you all this one. It means that if we do a uniform partition, means that intersection, it's very close to optimal. And the approximate ratio is 1 plus 1 over n. Well, m is total number of copies. The reason is that you don't have this optimal result because when you do pipeline, you cannot really fully align. I'm not going to show this one, just show this diagram. In reality, it should be like this kind of structure. It means that you start with computation, then communication, computation, communication. So it's not really aligned, right? But then do we come up with some result, in certain situation, you can even get the optimal result. So, but this is a little bit too much involved, so I'm not going to discuss it this one. And we have over a little more extension on which condition you can get the optimal result. And we conduct this experiment and compare with the real optimal result, which is brute force. Means that this still kind of approximation, very close to optimal. But you can see that all our results on different experiment very close to the brute force one. And this makes sense. And we have also some extension. Right now we look at the like a linear line. So people say, oh, this may not be too practical because we assume it's linear. And we can extend it to the tree structure, like a multiple paths. So if you're interested, you can look at one of our publications this year's IWQS. So the next few slides, which I think is even more important in the sense that how this make it practical. And in fact, we wrote the proposal and get funded this year. It's NS medium size. NS medium size means it's $1 million grant. So with several universities, so we have experts from Stony Brook on the computer vision. And my former student at the Caitlin University, which is GM College. So they have a special track. You see this right diagram? On campus, they have a real track. So you have a car really doing this one. So our idea is like using out this kind of theory to real practice, means that can you deploy some of those kind of sensor, like IoT device on car and doing all this kind of image analysis in real time. So this is our funded proposal. And obviously before we doing this real test bed on the real track, we have some kind of toy device, and this is built by the another university, so our partner. So we install some of this stuff, a sensor on this kind of toy, a car, before we do the actual deployment. And there's even more interesting. There's like food for thought, some reflection. So far, the interconnection network we look at is very structured. Right? Structure means that all this DNA is a linear or multipath or DAG. And believe it or not, someone in the AI community or image processing community, they study, okay, can we just do this one? We look at any kind of network, kind of random wired neural network. Will this be effective? So this is a kind of interesting paper, ICCIT, one of the top conference in the image processing 2 years ago. So the one group studied this one. Right? So you have a different type of random graph. Right? So you have a traditional Erdős random graph or like a small world graph, right? So what's small world, and so on. So this one is just kind of interesting. Maybe this is another field, because in the past, like 30 years ago, I did lots of work on the interconnection network at that time for the parallel processing community. But now maybe this neural network community can look at the different type of interconnection network. So I think with this, my time is up. I still have 5 minutes, maybe like a question. I just want to acknowledge some of the collaborators, actually both of my former student. One is Professor now at Rowan University in New Jersey. He's one of the 4 schools we're doing this NS project. And my PhD student who's doing the implementation, he was recently hired by Facebook, and we join Facebook next year. Okay, with this, I just conclude today's talk. Again, I apologize that since it's only like 45 minutes, some of the detail I have to skip. So I just gave you some basic ideas, like how to go back to the basic, like the scheduling, then how you make it more practical. Eventually, our ambitious goals for this kind of deployment in the real application. Okay, with this,
right.
Thank you.
Thank you, Dr. Wu. We really appreciate your taking time so late in the night in the US. So I'm surprised that you didn't fall asleep by now.
Actually, I got up very early today. It's like 5
Right,
o'clock
right.
in the morning. Yeah, working.
All right. I think we have 2-3 minutes. So I'd like to ask the audience, maybe we'll take 2 questions. So if you want to ask any question, then please unmute your phone and say that. I'll not be monitoring the chat box. So please go ahead and unmute your microphone and then you can ask the question. Anyone?
Yeah.
Any questions from anybody?
Maybe it's still early in the morning in Bangladesh.
Very early, actually. It's about 10:15 a.m.
10:15. Yeah.
Should be awake by now. So it seems there are no questions from the audience, but I just want to make an announcement on behalf of Dr. Wu. He has lots of funding from National Science Foundation, as well as other agencies. This is an opportunity for students, especially who want to pursue a PhD degrees in electrical engineering, computer science, or in computer engineering, to get in touch with him, see whether you can find a topic that matches with the interest of Professor Wu. That is actually one of the reasons we invited researchers from the US so that you can get connected. And as I understand, Professor Wu is very happy with the students that he worked from Bangladesh. So we have a minute. Still, if you want to ask any question, please go ahead.
Yeah, maybe I just follow up with Mohammed. So thank you for doing this advertisement for me. Yeah, actually, I recruited 2 Bangladesh students. They're both very successful. One actually graduated from China. So I hired him as a postdoc. Now he's like professor in the Fulton University in New York City. Very successful. He's like a highly cited now the scientist. And another Bangladesh student from the also recently graduated and joined the Penn State as a professor. So I'm very happy with the student from Bangladesh. So just recent 2 students, I was so happy. So yeah, that's why I approached Mohammed and see if any student, or if you're faculty, you can just contact me or recommend some students. Thank you.
Well, thank you, Jai. Again, let's give a big thanks to Professor Wu through the cyberspace. And we look forward to connecting with you.
Okay. Thank you. Thanks for inviting me.
Thank you very much.
Yeah.
All right. Let's move on to our next keynote address. The speaker is Professor Atiquzzaman. He is the Edith J. Kenny Gallard Presidential Professor at University of Oklahoma. Let me see whether Professor Atiquzzaman is in or not. Okay, let's see here. Dr. Atiquzzaman, are you in? There are lots of people who logged in, so I'm trying to see whether I can find you here. Let's see here. Okay. Atiquzzaman, are you in? Okay. I'll probably give him a minute or so. If he doesn't log in, then we'll move to the 3rd keynote. But we did send him a reminder last night and this morning also. So let's see here. All right. In order to stay on track, what we'll do, we'll move to the 3rd keynote. And if Professor Atikuzaman comes back, he'll present his talk on the in the slot for third keynote address. So our next keynote speaker would be Dr. Thomas Lu. He's a senior researcher at Jet Propulsion Laboratory at the California Institute of Technology. And in fact, Dr. Lu have been working together for organizing another conference in the US, and he has been contributing a lot to that conference also. The title of his keynote address is an expandable AI assistant for the first responder driver safety. With that very brief introduction, I would invite Dr. Lu to present his keynote. Dr. Lu, please welcome. Go ahead.
All right, thank you. Thank you, Professor Lam, for your invitation. And this is an honor to give a presentation in the ICCIT conference. Again, my title is Explainable AI Assistant for First Responder Driver Safety project. I'll first acknowledge my collaborators. We have a big team. Dr. Edward Chow is the program manager at NASA JPL, and I'm the PI and the project manager. And we have two leads, Dr. Yun and Mr. Huyin, a bunch of students and other collaborators. Again, Temple University, it's famous. We just had a speaker from Temple University, and here is Dr. Pei Wong collaborated with us. And then we have also Miami-Dade Police Department collaborating with us to test our system. And this project is funded by US Department of Transportation. All right. So the outline will be, first I'll introduce the TruePaw technology. It's trusted and explainable AI for saving lives. So we call it TruePaw. It's a AI assistant for first responder safety. And I'll give a TruePaw project overview and the system architecture with multiple components. And then I'll talk about the explainability research as the key part of it, and also the app with human interface and some demonstrations. All right, first, why this project? Because estimated emergency vehicle accidents in the United States cost over $35 billion annually, if you believe that, because there's a lot of lawsuit and all this kind of human life loss. Fatality caused by collision are almost 5 times higher than the national average by the first responders. And police officers have roughly double the rate of motor vehicle crashes per million cars than the general public. And it's actually not during the high speed chasing. It's mostly during their routine patrol, they have got into accident. So we have found that the digital alerting has shown promise to avoid roadside collision. And the Congress last year has appropriated the Department of Transportation to study this problem and then come up with some solutions. So we are one of the research organizations conducted this research and come up with a system. So first, we can see that this is a typical police vehicle cockpit. Because of technology advancement, you have more and more instruments in the police vehicle, and they are just scattered around. And can you believe you still have a computer screen and a keyboard and also a mouse? So you can imagine that when the police is driving, he's typing the name and the address of a suspect and then try to find the information. So that's why it gets so much information coming in that it just distracts the attention from the driving. All right. So the idea here is to develop a true assistant that can assist the police to focus on driving. So this is the system we come up with. We have this true system that can take all those information and then perform adaptive learning, reasoning, and inference, and then give you a 360-degree situational awareness and risk assessment, and then prioritize the action recommendations. Because we need to prioritize it. If there's a danger of crash, then we need to immediately tell the police. All right, then we have some kind of interface that can be easily communicating with the police. All right, the goal is to help drivers to reduce accident. Here is a use case that we come up with the help from the Miami-Dade Police Department. They are a very big police department. They have a lot of crashes every year in their department. So they have done studies of where and why the police get crashed. We come up with these 5 scenarios that we want to test TruePaw. So first is the intersection, of course. Now, the scenario is there's a big crash. There's a big truck overturn, and there could be some chemical spill. So that triggers multiple agencies rushing to the scene. So we have a EMS, we have a fire truck, we have police, and maybe we have some rescue team coming to the scene. And we want to make sure that they come to the scene safely without their own crashes. So first is intersection safety. So how can we pass some intersection without causing crashes? And then roadside safety. So when you park on the roadside, you don't want to get into crashes too. And then there's a hazardous sign ID because there's some chemical spill. So we want to quickly guide the first responders how to deal with this chemical spill. And then first aid, if the EMS has not come yet, so the first responder has to try to help those people get injured. So what to do with those injured people? And last one is a recent problem is we have more and more electric cars involved in the crash. So how do we handle electric car? Because it has a very high power battery in the car. So it's be very careful. Otherwise you get shocked by the battery. All right, so these are the scenarios we need to solve. Okay, so this is a very simple illustration of the system. So first we have a driving simulator because we don't want to test our system right in the street because it can cause more accident and crashes by itself. So we have a driving simulator. It's called Kala. This is actually a very good simulator for autonomous driving. They built this simulator. Then another part is called the deep neural net. That's basically taking care of object detection and the tracking. And then we have a AI system. This is called NAS. It's a non-axiomatic reasoning system to help resolving issues and giving recommendations. And the last part is the app that can help communicating with the first responders. This is a little bit more detail. Again, Kala simulator gives you camera video frames, radar, LiDAR, GPS, and all this sensor information. Object detector takes all this information and then track all these objects, moving objects and the stationary objects. And then tracker gives speed, acceleration, location, direction, and the prediction of different collision. And then this NAS reasoning system, taking also from a knowledge database about the priorities, traffic rules, and all this type of information, and then give warning, either collision or any other warnings. That sends to this web app. The app is in the on the cell phone, so you can communicate with chatbot. So you can do chats with the first responder. Okay, so the Kala simulator is actually a very good simulation software that give you very realistic kind of 3D simulations. So you can see it can simulate sunset, rainy, cloudy days. It can different locations. You can also map it into your own location. So you can create 3D objects, 3D scene, and then map your map into this 3D environment. So it's very convenient system. It's an open source system. You can make your own customized traffic patterns. So like this one is no, we just run this program. It gives you kind of a simulation of different traffic patterns, and then you can do it. And we also simulate a lot of a real kind of a collision. Like on the left side is a video of police got hit by a car not stopping on the stop sign. So this side is how we simulate it in the color. And again, this one is in the snow, although we cannot see snow here, but it's kind of very bad weather. And then there's a truck coming from the left and then hit the police car. All right, so and again, this is another, it's very hard to see from this video, but this is a simulation from this color. And here is simulating high-speed car hitting the police car in the rear when he's parking on the road. Actually, this is one of the killer scenario that every policeman is afraid of when they make a traffic stop on the roadside. A lot of times drunk drivers or people don't care about, just hit them. All right, so this is a very big problem they have. So we'll talk about the object detector and the tracker. One big thing is to train the deep neural net with a lot of training samples, which is very, very time consuming to manually label it and then manually prepare the training samples. Here when we use this color simulator, we made an automated process of generating all these labels and segmentations, automated it. So it's very quickly we can generate all these pedestrians, traffic light, traffic sign, vehicles, many of the thousands of them quickly, automatically. And then we can train the neural networks to recognize objects. And then we test it with real videos. Actually, they work quite well interchangeably. And we also test the video and the different modalities. And this is testing drunk drivers when there's a weaving car, how far away we can detect it. Because we want to detect the weaving car or any car in kind of the danger as far away as possible so that we have enough time to warn the first responders. For video, we found video sources only detection distance is 150 meters. If no, it's in the line of sight. All right, so 150 meters. If you are in a freeway or highway situation, you don't have a lot of time. It's probably like maybe 3 seconds to 5 seconds. Right? But it's better than nothing. Then we also combine it with the radar. Radar can detect further away. So we tested the radars around 321 meters. If you can see the car, okay, if it's not on the other side of the mountain, then radar really extended the distance to much further away, right? So we do use both radar and the video to detect objects. Then one big part of is the explanation, explainable AI, which is the reason we want to make it explainable is this is a very kind of a high tempo, very life and death situation. So the first responder has to trust the AI system. Otherwise, they don't want to use it. So how can we trust the AI system? So make it explainable. All right. So it's like when you first time working with someone, you always make sure that why you want to give this recommendation or why do you want to make this decision. You have to explain it until people trust you. Right. So this is what we do. And we talk about a lot of deep learning. We use deep learning a lot, but deep learning has a problem. It's a very complex system, like Professor Wu just talked about. There are many layers, and then there are a lot of interconnections, a lot of weights in between layers, and you really don't know what's going on. When you give an input, you get an output, and then you don't know what's really happening inside this black box. So it creates a lot of problem, especially for like NASA, because NASA has to test everything, 100% testing, because we cannot repair it in the space on Mars. So that really really makes it very hard for like deep learning to be used in a spacecraft. So this is one example, like YOLO V4 has 140 hidden layers and 20,000 filters in the backbone. So there are a lot of convolutional layers over here, and then also dense layers. It's actually comparably a small neural net, compared to other like the ResNet and all this, getting more and more. All right. So what we are doing is here is we open it up, and then we basically search through all the layers and every filter, and then see which one is responsible for which feature. All right, so we do a map, activation map. What we did was, let's say we have a car, and we separate the features and then test the system, which neuron is responsible to which feature. For example, this is a car, and this is a car without wheel, and this is a wheel without car. All right, so we test all three of them in the system and see which neuron and which filter activates when you see this one, or this one, and that one. And then you can see here, this is a filter activation map. So when the filter sees the wheels, it gets activated. So you see the red one. When we take this wheel apart, hidden it, and then it's not activated. So you can see very clearly this filter is responsible for detecting wheel. All right. And then we tested with different cars in different location, different position. You can see that indeed this filter always get activated when there's a wheel. Of course, it has something else. We don't know. It's not just for wheel. It's looking for something else too. All right. And then we also find different filter, like this filter 610 is responsible for license plate. So you can see the license plate, when it shows up, it get activated. So with this kind of a mapping of activation, we can look into the neural nets, every neuron, every filter, what is responsible. For example, this particular neuron, you can see it's responsible for some type of vehicles. And this particular neuron is responsible for giraffe for some reason, these two neurons. And then this one is like for windows. There's a window, even this monitor looks like a window, so it's activated. So with that, we can create a map of the neuron and then explain why you get this car. Let's say we see this car, we say this is a car, but why is this car? Because there's a wheel there. Even the car is half blocked. For example, this small then you probably blocked most of the car, but it does see the wheel, then it still get activated. So when you ask why you give a car, because you see a wheel. All right. So with that, we can do systematically mapping the activation and the inhibition neurons. Some neurons inhibit a particular features we want to know, and then enhance the prominent neurons, and then we can prone the neural net so that the lower ranked neurons can be proned without affecting the performance of the neural net. Actually, in one experiment, we proned 95% of neurons. The performance even get better. You see, this is really interesting because when you have smaller neural net, you can retrain it. It becomes more efficient, more effective, right? And you can do self-organizing because you can recombine features to create a new output class. That is very powerful because now you have all the features, you can recombine them, even you didn't train on it, right? Especially when you're doing exploration. Let's say you are doing exploration under the ocean. You never see a creature. That creature has a crab's leg, but it has a fish fin, right? You never train a network with that. But if you know you have this features of fish fin and the crab's leg, now you can say, okay, we find some new creature that has fish's fin and crab's leg. All right, so that becomes a new category. So it increases explainability and also increases testability, so that eventually, we increase the trustability of the system. So this research is very interesting, still ongoing, and DARPA is also very interested in this type of work. All right, let me give some examples of this system. You can see that this is a intersection. Okay, so it sees all these objects, and also it detects the traffic light, and then it maps into the database that this intersection has a lot of accidents in the past. So it gives a warning to the first responder that you have to slow down. You can see that the warning here. Street is risky and the street is on. So this is actually the AI talking. It's not exact, English, but you can understand it. So street is risky, and the street is on means the traffic light is green, but you need to slow down. So just warn you, this is a risky intersection. Right? And this is another one giving warning. There's a red light. If it says self, so you are above 35 miles an hour, so you are too fast because you are approaching a red light, but you are more than 35 miles per hour. So that give a warning. You need to slow down. Right. This particular one, actually two first responders approaching the intersection at the same time. So they, through the radio communication, the TruePol knows that there's another first responder coming from the cross street. So it warns that intersection next is approaching and intersection next is expected first responder. So basically it says there's another first responder coming in, you need to stop, let the other people go. All right, so then the first responder stopped, and then the other first responder pass, and then you can go. All right, so these are the we have 24 different scenarios in the first in the intersection, and just some examples on the roadside, which is a very the policemen are very interested in that. This particular one, this car is driving too fast and is in the outer lane. So you can see that it's about the 2.7 seconds before it approaches. Then it says car 8 is fast lane. Okay, it's in the fast in this lane. So it gives a warning like 2.7 seconds before it hits the first responder. So 2.7 seconds is not a lot of time, but no, at least it's enough for you to jump out. All right. This is another one. This car is weaving. You can see this weaving. So maybe this is a drunk driver. All right. So TruePaul finds out this guy is weaving and then give a warning around 7 seconds before it really hits, right? So it's already car 5 is weaving. It sometimes gives a different number because depending on which car, how many cars are in the scene. So it's basically track this one and say this car is weaving. All right. So it gives enough time for first responder to really be aware of it and then do something. Okay. Next part is this TruePaul app. It's very important to have a very good communication with first responders because you only have a few seconds or even less than a second to give a warning. So you need to give a really good communication and build also trust. So here's the architecture. We have backend database in the cloud, and then we have NAS agents. So those are the first responder agents in the system, let's say in the vehicle or somewhere. And then we have mobile app. So it's on the person. So he can carry this mobile app with it. So you have a small TruePaul agent here. We have a really larger TruePaul agent there, and we have a even larger TruePaul agent. So we have different levels of TruePaul agents. The TruePaul will give you a voice control to give a voice command, and then notification in the alert system and a push notification. So here it shows. I don't know if you can hear it. This actually just give a talk, but let me show some more. This is the map that it shows all the first responder vehicles and also first responders. If you are not in the vehicle, it tracks everyone in the map, so you know where everyone is when there's an accident happen. And this is we integrate them together, so you can see that this is actually. Do you hear the warning voice? It's actually there's a voice said warning, warning when it shows this. Yeah, and it shows the two first responder vehicles crossing each other, so you can see that. And this one stopped and then let the other pass. Right. It also gives a verbal warning to the first responder. All right. This is again another that warning. Oh, this is the same. All right. So this is the roadside situation. It has I don't know if you can hear the warning voice, but it's let me see if you can hear the voice.
Warning, 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 warning.
Can you hear the warning voice?
Yes, it was.
Okay. All right, good. All right. This is again the
warning, 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 warning.
So it's keep
Warning.
saying warning because no, we can say more about, but first, we need to just give a very simple warning voice to the first responder because no, they need to do something, right? And then we can make it more sophisticated later. Now this is again the same. This is
Warning, 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 warning,
okay. It's hit.
warning.
All right. This is for the hazard sign reader. We have a deep neural network to look for the sign from a truck or from the vehicle, and then recognize this ID code, and then give you a guidance. Let's say over here you can see. So first, look for these signs, and then recognize the label, and then give you the guidance. Right. So you basically take a picture of the vehicle, and then the TruePaw automatically look for this sign and find the code, and then give you the guidance. It grabs a guidance from the database and then show you what to do. This is just show this is a vehicle, and then sign, and then give you this number, and then give you the guide. The guide ID is 154. So it pulls out this part of the text and it shows you. This is to talk. No, you can just give a
Getting the test version of AI chatbot. Please say the 4-digit UNI. 1016. Searching for the UNID 1016. This is for guidance 119. Category: Public Safety and Subcategory.
All right. So it basically
Our tank truck is involved in a fire. Isolate for 1,600 meters, 1 mile, in all directions.
Okay, so this is a hazardous sign detection and also give guidance. This is a demo for first aid assistant.
Talk to AI chat.
Okay, getting the test version of AI chatbot. Please say the 4-digit UNID number for hazmat placard.
A man 40 years old on scene appears not to be breathing, not moving, and not responding to any stimulation.
For hands-only CPR, place the heel of your hand on the breastbone at the center of the person's chest. Place your other hand on top.
This is actually not music. It's simulating the the sirens. Like you can hear it, right, Professor Alam, right?
Yes, yes.
Okay, good. Sometimes I don't know if people hear it or not.
No, they're hearing.
Okay, good. Okay. Yeah, the last one is recognizing the electric vehicle. So this is another conversation between the first responder and the TruePaw chatbot.
To AI chat.
Okay, getting the test version of AI chatbot. Please say.
We have a car vehicle accident involving a 2015 Tesla and 2016 Honda Civic on the 605 freeway.
comment. There are no specific procedures for dealing with electric vehicles, but be aware that the batteries contain high voltage and improper handling can be dangerous or lethal.
All right. So this is a electric vehicle. DOT want this as a placeholder because they are still developing guidance for how to deal with the electric vehicle. But first, we have to be aware. It's a different type of problem that we have to deal with. All right. Okay. So actually, in Steinbury, what we have developed here is a AI agent, or we call it AI assistant. Its name is TruePaul, a trusted and explainable system that can save lives. So we demonstrate the capability of crash warning in simulated scenarios. So next step is we use real videos. It's much harder to use real videos because it's hard to collect those videos. So that would take a longer time to do. But the simulated scenario looks very successful. The TruePaul AI tool has shown preliminary capabilities, human-machine AI interface, and then during the intersection roadside, actually roadside cruise is something that's really interesting. We checked with the DOT. Every year there are about 700 people get killed during around the construction site. So actually, it's average like more than 2 people per day get killed because of people don't pay attention or things like that. So this system can really help on that. AI-assisted dynamic generation of complex traffic scene. We did that, and also generating simulated training samples and testing samples. That really help to test the system with less physical track tests. Also explainable deep learning capability so that we can explain it to the first responders or users or testers to build trust from this AI system. All right, I'll stop over here and then hand over to Professor Alam for question and answer.
All right, thank you, Dr. Liu. Any questions for Dr. Liu? As you know that JPL has been involved with all the research activities associated with NASA launching vehicles, tracking them, monitoring them, and also some of the things that Dr. Liu just mentioned. So with that, let's see whether we have any questions from the audience.
Hello, I'm Dr. Aslam Rahman. I want to ask you a question.
Go ahead.
So you talked about explainable AI, like if I understand it correctly, it can detect which neuron is doing what, which neuron is responsible for what. So can you please elaborate more, like how does it know which neuron is, like what is the mechanism? How does explainable AI knows which neuron is doing what?
Yeah, in that actually we have a training sample set, right? In the training sample set, we partition those training samples. I showed one example that a wheel is a good feature for recognizing cars. All right, so we take the wheel out, and we can show which neuron is activated by the wheel and inhibit the wheel. It's the same thing. You can generate features from the training samples and then use the features to test which one of the neurons is responsible for a certain type of features. And then you can map that. Also, you can just by putting the training samples in and also cut part of it and then you see what's the response of the neurons. All right. By doing that, you can map the neurons into a activation and an inhibition map. And then that's just one of the methods you can use.
Okay, any other questions from the audience? Any other questions? We have a few minutes, about 3 to 4 minutes left. This is a good chance to ask Dr. Liu. They're involved in state-of-the-art research work, simulation, and things like that. Any other questions from anybody, especially if you work in deep learning neural network, probably this would be a great idea or great time to ask somebody who is working directly in that area. Okay, I don't see any hands up or anything in the chat box. So Dr. Liu, I want to thank you for taking the time.
Okay.
And it's obviously
Thank you so much.
on the weekend, but we truly appreciate your time for connecting with us. So I'm not sure what happened to Professor Atikuzaman. I assume he has an emergency or something. So our last talk actually will begin in about 45 minutes. And until then, I would probably ask you to take a short break. And in the meantime, if Dr. Atikuzaman shows up, I'll put him back in this session. So we tried to connect with him by text, phone, and other things. He's not picking up. So I assume that he has probably an emergency kind of situation. So let's take a short break and we'll connect back with you in about 45 minutes. In fact, I sent a message to the last speaker, so let's see whether we can bring him on board. So if you stay tuned, I'm communicating with the last keynote speaker. Let me see whether he can come on board, so that way we don't have to wait for 40 minutes.
Thanks.
Okay, Dr. Guizani, who is the last speaker, he's trying to connect. So as soon as he connects, we'll start the last keynote. All right. So I say, Dr. Guizani, sorry, I had to wake you up. One of our keynote speaker didn't show up. So we have like the entire audience on standby for you. All right. Can you hear? Actually, I'm not hearing you. Okay, great.
Yes, I can hear you. Yes.
All right. So Professor Guizani has a long, distinguished career. He has published over 500 or 600 refereed journal and conference papers. He is also a fellow of IEEE. So with that brief introduction, I would ask Dr. Guizani to proceed with his talk.
Okay. All right. Can you see my slides?
Yes, we can.
All right. Good, good. Good morning, good afternoon, good evening, everyone. Thank you for inviting me, Professor Alam. My talk today is about the use of machine learning and Internet of Things in different IoT applications. And all right. So the outline of my talk is to first motivate this work and then select a few projects to talk about the findings and concentrate at the end on a few open research topics. So IoT is coined, as probably you know, by a professor at MIT, Kevin Ashton, in 1999. And since then, as you can see, the market share of Internet of Things has grown exponentially. And then artificial intelligence has been around for a long time, since the 50s. And as you can see in this chart, it has evolved and has included deep learning, machine learning, NLP, and machine vision. And the IoT edge or fog computing has also been used since 2012 and has proliferated in different applications. So the enabling technologies of these have been that the fact that there are IoT devices, as you can see on the bottom of the slide, that they are collecting data from different applications, and then in the normal circumstances, this data is sent to the cloud and is processed and then analyzed, and decisions are made by experts for whatever applications that may be. But then in certain applications, emerging technologies, for instance, the delay to the cloud, so sending the data and storing it in the cloud would create a problem. You know, for instance, if we have a remote surgery, then we cannot tolerate the delay the data being stored in the cloud and having a slow network. So people start thinking about the edge or the fog technology, where the edge is trying, as you know, to get the cloud closer, or parts of the cloud closer to the users and closer to the data collection parts. So in some of our work, we coined what's called pervasive AI, pervasive artificial intelligence, where this type of artificial intelligence is used in distributed inference for IoT security, for multi-drone surveillance, and applications also for distributed learning as well, where we have federated learning for IoT and multi-agent reinforcement learning for that matter. So in a situation like this, for instance, like you see in the slide, we are again collecting the data from a smart city, as you can see on the bottom, whether be it autonomous cars, emergency vehicles, surveillance of the streets by certain cameras or UAVs, as you can see here. And then that data is collected, as you know, and this is sent to the cloud to be stored and analyzed, and then decision should be made. This is the normal circumstances, the normal situation. In this situation, as you can see, we have a number of challenges. They are listed on the left side here. Scalability is a problem because, as you know, the number of IoT devices is increasing by the day. I mean, we expect the expectations that by 2025, the IoT devices will be scalability will be a problem because the IoT devices can increases by the thousands, if not tens of thousands every day. Storage is a problem. So the data that we collect is raw data. There is no pre-processing or pre-cleaning, and we send it to the cloud, and then we store the whole thing until it is processed. So we may face problems of storage. In turn, that data which is raw, that is sent through the network, as you can see in the middle here, it can cause bandwidth bottleneck, or it can cause bottleneck situations where we cannot, the network cannot cope anymore with the huge amount of data that is being collected with the increase of the IoT devices on a daily basis. Energy is also it can create a challenge for the energy because, as you know, there is energy is a constraint parameter in these IoT devices. They are not these IoT devices may not have enough computing power, may not have enough energy, may have problems with security and privacy, and so on and so forth. So these are some of the challenges that we could face in a situation like this. So in that situation, in order to mitigate these challenges or these problems, one can introduce what's called an edge device. As you can see here in the middle, we have introduced the edge device here. The edge device, its role is to get the data from the IoT devices, collecting the data from the smart city or from certain environment, and it can have some pre-cleaning rather than sending the raw data to the cloud. So the pre-cleaning or the pre-processing at the edge device will help, as you can see. So we have brought the edge device closer to the user, closer to the IoT devices, which mitigate some of these problems. We also have introduced a pre-cleaning or pre-processing at the edge devices, and therefore we have mitigated some of these challenges that we listed in the previous slide. Scalability is no longer a problem because we are controlling the increase of IoT devices by the edge device. Storage is no longer a problem because we are no longer sending the raw data to the cloud. We are trying to pre-process and pre-clean it at the edge device. Bandwidth is no longer a bottleneck because the network is relieved now because of we are not sending the raw data through the network. Energy is, and so on and so. And security and privacy, we are no longer sending the raw data where it can be attacked or eavesdropped at the network or at the cloud situation. So we are no longer having these challenges. But with this, we introduce new challenges. where the new challenges are as listed here on the right side. The new challenges are deployment complexity. So that means how we can where would we place these edge devices? Are we going to introduce them where? At what level we can? Are we going to be able to convince the companies that provide us with these services to be able to install new devices that will be more expensive for them? The infrastructure is also a new problem, new challenge. The limited resources, we have some limited resources, as I mentioned earlier, in the IoT devices. So we have some new, we have mitigated those old challenges, but we have introduced some new challenges that are so then we can in order to improve the situation, we can or mitigate some of the new challenges here. We can bring these edge devices closer, more closer to the user, as you can see in the slide, where the edge devices are selections of some of the IoT devices. You can see here the edge devices are now within the edge devices that we are using, within the IoT devices that we are using to collect the data. So we can select what we used to name as cluster head in the sensor networks. Remember, in the old research that we did in the 90s about sensor networks, we elected a sensor head or a cluster head, where the cluster head is a device that is more capable, more involved, more it has more energy, it has more computing, and so we can elect some of these IoT devices to serve as the edge devices. So we no longer have that situation of the edge, where now we resolve the deployment complexity and the infrastructure. We no longer have a new layer of edge devices, but we still have some limited resources. So the situation here now is communication versus computing, or computing versus communication, where we have it's a trade-off between communication and computing. That means how much we can compute so that we can be successful in the communication part, or how much we can communicate so that we can compute less, so that we can save energy and save. So this is the motivation, or this is the new paradigm of pervasive computing. So pervasive computing is how to smartly distribute computing and communication. What is the trade-off between them? As you can see here, so pervasive edge computing is how to communicate less so that computing is better, or how to compute less so that communication is successful and much more rewarding. So it's communications meeting computations, and combining the pervasive edge computing with artificial intelligence brings us the new paradigm of pervasive AI paradigm. And examples of these are data cleaning, for instance, and pre-processing. Remember, we want to do the pre-processing and the data cleaning. So before we send the data to the cloud, adaptive compression. If we have images like what's happening in the COVID-19, we are collecting images from the lungs or parts of the body and sending it. We have to make sure we compress those images so that we don't overload the network. Feature extraction. So we're no longer sending the raw data. We are doing feature extraction and sending only the features, as we will see in this talk. And then state detection, prediction, and classification, ensuring security and privacy to prevent reverse engineering for these. And then accessing network selections. We have to select the proper network so that we can be able to achieve this. So pervasive computing is divided in two different types. It is one type is called pervasive inference, and the other is pervasive learning, as shown in this diagram. And then in pervasive inference, for those who are looking for new ideas for research in this area, pervasive inference is still a new area, and there is not much available in the literature about pervasive. CNN, for instance, convolutional neural network, segment-based and layered-based, for instance, being used in security or surveillance, being used in drones and collecting data about the smart city and so on. On the other hand, pervasive learning has been researched for a while now, and there is a lot of information about federated learning, as you know, and multi-agent reinforcement learning. So today we'll talk about some federated learning applications and some multi-reinforcement learning. For the sake of time, we'll just talk about 2 or 3 applications projects that we are working on. So here the objective in this situation is to use optimal distribution of machine learning model among these IoT devices to minimize latency, because remember, latency in certain applications is really very important. The challenges here are the resource limitations in these IoT devices, limited computations, limited memory, and limited energy. As you all know, these IoT devices, they are very heterogeneous, and they don't have enough computing or enough storage power or energy for that matter. So the challenge is security and privacy. We want to make sure that no reverse engineering is made so that we can crack the system, and the choice of the network is dynamic. That we have to make sure that the network is dynamic enough, or mobility does not affect the application. So for instance, we have used this in an environment like this, security and network surveillance, for instance, where cameras or UAVs are collecting data images. In this case, as you can see in the original image, the surveillance camera has captured this image of a person, where we are looking at, we're searching for a person, or we want to recognize the people who are coming to this building, so that we don't have any problematic personalities coming in and making any trouble. So the original image is captured and is sent to the convolutional neural network, as you can see here, or the convolution deep network, and we use segments here to segment this image, and then get the information using black box malicious participants, and invert the image so that we can make sure that we recognize these use face recognition. We recognize these people and make sure that they are. And so this is one applications that we have done. I won't talk about the details in this application because of the time constraints here, but our publications are listed on the bottom, as you can see. And if you have any further questions at the end of the talk or later on, you can send me emails and we can brainstorm on that. So now we can move to the drone surveillance. In drone surveillance, we don't use segment convolution network or the segments. We use layers in this situation. And as you can see here, we have drones surveying a certain location, certain part of the city, and then data is being sent, or images are being captured and being processed in a layer base, as you can see here, and then we use the convolutional deep network again to process the data and find out the needed information to make the right decision and to be able to use autonomous systems in this situation, and make sure the autonomous is secure and next we want to talk about federated learning. In this project, I will talk about some more details of mathematical modeling and how we achieve this. So in this situation, we have a normal situation. You have the IoT devices, as you can see on the left side. They're collecting data and they're sending it to the cloud. So this is the normal situation that we usually have. But then in federated learning, we don't, individuals cannot share their data for privacy, and in order to enhance scalability, we don't want to send the whole data as the situation. And then in order to enhance, we want to enhance accuracy through collective wisdom. So in that situation, we don't send in federated learning, we don't send the whole data here. We send what's called machine learning weights or represented parameters only, rather than sending the whole data. In that situation, as you know, we want to have we'll provide security and privacy to the data, because we are not sharing the whole data with the cloud. We will reduce the storage challenge. We will reduce the bottleneck for the network, and so on and so forth. So in a situation where we have federated learning, the situation is represented as such, where as I said, the edges, these edge devices, these cluster heads that we selected, okay, they pre-process the data. We are no longer sending the whole data or sending the raw data to the cloud. As you can see here, we're sending only weights, W1, W2, and so on and so forth, and from the edges. So the edges do some pre-processing, whatever that pre-processing or pre-cleaning is, and sending the weights to the cloud to process the weights, not process the whole data. For instance, let's take an example here to elaborate further. So the weights, if we have certain applications, for instance, applications, let's say medical applications. Let's say we are searching for heart signs of heart disease or signs of heart failure. So we have some devices in certain locations of the city, or for certain number of people. We're collecting signs of heart disease. So the signs of heart disease that are collected from this portion of the population will be different from the signs that we collect from D2, D3, and so on and so forth. So we send only those signs to the cloud. We don't send the whole data. We collected the data. We pre-process the data in the edge here at W1, W2, and so on. We collect the W's, the weights or the signs, and send only the signs to the cloud. The cloud will do what's called a federated average. We'll take all of these weights. We'll do a federated average. That means we'll combine all the signs that are coming from the edges, and we'll send an average weight parameter to all these devices, to all the edges. Okay, so the federated average, the weights that is coming to the edge, represents all the weights that are collected from the different edges here, and therefore there is more information will come back to the edge device from the cloud, telling it about the more signs of the heart disease. So with this circulation, we do this multiple times and recursively, so that the process or the accuracy improves. So we start with the accuracy of maybe 30-35%. We routinely do this process for multiple times, and then we learn every time we do this process, we learn more recursively, and therefore until we reach a certain accuracy that is acceptable. So once we reach an acceptable accuracy, then we call that collective wisdom, because the wisdom we collected is based on different parameters that we have collected from all these devices. There is the example of the heart disease signs, or any other signs for that matter. Another example is communication company or your service provider wants to collect data about the users, its users. So it wants to know what are the usage, what are the appropriate usage for the service that different portion of the population are using. Are they watching movies? Are they using the internet to watch movies? Are they downloading information only? Are they surfing the internet only? Are they watching watching only YouTube, and so on and so forth? So they can collect all of this data, and based on the collective wisdom here, this recursive process, they can. So with this, we have learned a lot about our users, but we did not overload the network. We did not overload the cloud here with sending the raw data. And then we have extended this process to what's called hierarchical federated learning architecture. So we have created a hierarchy here. In addition to the edges here within the smart city, we added another layer of edges here. As you can see, edge 0, edge 1, and edge 2, and the hierarchical. We turned out that the hierarchical situation, its objective and challenges. Its objective is to optimize the model sharing to speed up the convergence. So you can see we went. The objective is to reach a convergence, to reach a collective wisdom as soon as possible. So the objective here for the hierarchical federated learning is optimize the model sharing to speed up the convergence process and maximize accuracy, because accuracy is important in this situation. We want to maximize accuracy in a short period of time, because we want to learn about these models as soon as possible. The challenges, of course, here is the data is heterogeneous, and we have to use a non-IID model so that we can process or analyze this data. The examples of the health I gave, or the broadband company service provider. The challenge is the network topology constraint also. So without going through the detailed mathematical model, I'll just give you a feel of the. In this situation, we are using distributed stochastic gradient descent, where we are minimizing a loss function based on the cross entropy, and the minimization for the cloud is the first equation here. Minimize the weights that we want to send, so that we can achieve an accuracy as fast as possible, and the weight is computed as such, the weight of the previous instance or the previous cycle minus some latency here, or weights that but in our hierarchical federated learning, we are using the second equations here at the user device U. We are using the overall here, minimizing the loss function of the cloud, but at the user level, at the device level, at the user level, or at the edge level, rather than at the user level. So we do the same minimization, the same weighting. We compute the same weighting at the device, at device U, and then we do the same thing at the edge M. So you can see here the W at M at cycle T prime is equal to the summation of the accuracy multiplied by the weighted of the previous. And then at the cloud, we now at the cloud we use the weighted computation value at the cloud at the edge, and we do that at the cloud, as you can see here at the last equations here. W sub m of f, it's not at t prime. The t prime is the cycle at the edge m. Now it's t prime cross t, so that we can find our computation or our weights at the cloud level. That's the weight that we will send down to all the devices, and we keep recursively improving. So our results, jumping to the results for the sake of time, our results are shown here in the slide, and our results are the yellow curves here, using the hierarchical federated learning. So if you compare it to the regular federated learning without the hierarchical, or the red curve here, or compare it to the cloud, which is perfect here, as you can see here in terms of accuracy. When you use the cloud, is the green curve here. So you can see that if we use federated learning, regular federated learning without the hierarchy, then you can see it goes, in order to stabilize or reach an accuracy here of 79 or 78%, we reach that at around 100 rounds here. 100 rounds of simulations takes a long time, as you know, for those who are using federated learning. So here, if we extrapolate this to the yellow curves where we used hierarchical federated learning, you can see that we can reach this accuracy in only 11 to 12 rounds, and the accuracy is 78–79%. And we can, in 100 rounds, we can improve this to 90, above 95%. So you can see that, and we use this. So you can see the improvement in terms of reaching the regular federated learning accuracy or threshold as fast as possible in 10 versus 100 cycles. And we use this, we achieved this in terms of two data sets, MNIST data set and CIFAR-10 data set. And you can see here that we can improve the accuracy, as you see in the table. We can improve the accuracy or improve the speed of the accuracy in terms of row. Row is the number of edge devices that an IoT can connect to. So the more edge devices that the IoT devices connect to, the better the accuracy and the faster is the speed. So we have really improved the situation much better, and therefore we have, without going through the more details, our results are published in the IEEE Transaction Network Science and Engineering for this year, has been accepted and appeared. So with that in mind, with that improvement of hierarchical federated learning in mind, let's move on to another applications, which is a smart health over 5G architecture. So we want to use reinforcement learning now for smart health. So for this situation, you have different patients here, or users, as you can call them, and you have a network of different sizes. This is the RAN network, whether it is Wi-Fi, 5G, 4G, 4.5G, 6G, and so on and so forth. And then you're collecting data. Data here is collected based on the patient state. The variables here are, or the random variables or random processes here are multiple. You have a patient state, you have a battery state, you have a network state. So we have different random situations here, and we are collecting these, and we are trying to choose the right network, the right RAN here, to be able to serve us better. So we want to make sure if we are using this to diagnose a certain heart patient, or we are following up with remotely with elderly patient. We are remotely trying to follow up with an elderly patient and making sure that they don't fall down or get a bad situation. So we call this multi. So you can see that the different types of states here, the patient state, the battery state, and the network state, can really complicate the problem and make it. So the objective here in such a situation, in this situation, the objective is to find the optimal action policy for the patient to minimize the communication latency and to minimize the battery life, to maximize the battery lifetime. We want, of course, these elderly patients to use the battery for as long as possible, so that we don't have to replace the battery more frequently. Find the optimal. Another objective is to find the optimal policy for the network level to maximize the resource utilization. Because the resources are constrained here, and we want to maximize them. So the challenge is that the policy depends on patient state. The solution is scalability, is distributed, is centralized, will not work, and therefore the problem is very complex. We have to minimize multi-objective function. Remember, the multi-objective function is based on energy, latency, cost, distortion. So there is a trade-off here. We have to find the optimal trade-off between all of these random variables. And we had to subdivide the problem into sub-problems and solve it iteratively. So to give you a feel of the solution, we have the adaptive compression, we have the distortion. This is the equation for the distortion based on a distortion element here, K sub I. We have the energy model modeling, which depends on the energy function here, plus a term here that represents whether the network is energy hungry or energy sufficient. And we have the latency model, which is a simple equation here. Here we have the problem is very complex here. We have to minimize a function here, which is based on utilization, where the utilization is based on the energy, as you can see here, energy I sub ij, plus the cost and the latency. So these are multiplied by some constants. In addition, we have here the distortion. So we have, as you can see here, this function is dependent on one parameter, the energy, 2 is the cost, 3 is the latency, and 4 is the distortion. So it's very complex in terms of solving the problem. So we have to subdivide it into subproblem 1 and subproblem 2 in terms of minimizing based on the distortion and based on the network and based on the distortion here, as you can see in SP1 and SP2, and then SP2 is still based on the distortion and the probability of distribution. So we can subdivide it into another subproblem 2.1 and subproblem 2.2, as you can see here. And it's the problem. The whole problem is subject to these conditions, which are related there. So since we are using reinforcement learning here, we have what's called the, of course, as you know, we have for distributed learning, we have reinforcement learning, we have the actions. we have the states and we have the rewards. So the actions, as you can see here, are depending on this distortion parameter, and the states are, as you can see here, the energy, the cost, the energy capital E, the cost C, the latency L, the distortion D, and then we add here two more states. This is the patient state, sigma, and tau, which is the network state, because we have two types here: the agent state and the network state. And the reward here is also, the reward is whether the network is on and we can process, or it's not, based on the patient state here. So if the patient is in a dire situation or is in emergency, when it is one here, if the patient is in emergency, then we have to spend all our values. That means energy. We don't care about how much energy we can spend, because we want the latency to be the minimum. So you can see here 1 minus the latency minus the distortion minus everything, because we want to spend all our resources in order to save the patients here. So that's the reward. So here, and then for the network, we can spend all the resources of the network so that we can save the. So here the situation, as I mentioned earlier, is complex somewhat. Here in the learning architecture, as you can see here, you have a complex learning architecture where you have a learning at the agent network and at the network itself. So you can see two learning types, and therefore we have the environment, and we have here the edge, which is related to the network, and we have at the end here the learning architecture. But this learning architecture is too complicated. So we can use some approximation to reduce the complexity a little bit to something like this, where it's called the deployment architecture environment, and we reduce some of the learning process. So in this case, we have talked about two projects: the hierarchical federated learning on how to achieve our accuracy in less recursive manner, in less time, and how to achieve also improve the accuracy and how to improve the speed of reaching the accuracy platform. We talked about reinforcement learning. One, the reinforcement learning is about how to give priority to those emergency situations where you can spend whatever resources you have in order to achieve a perfect situation and save the patient. We can of course for extensions, potential extensions of these is you can look at adversarial machine learning. Adversarial means that you have to make sure that your data is intact, your data is pure. It's not played with, whether intentionally or unintentionally. And there is an example in this paper that when we use data that is played with, we can get into problems of machine learning recognizing a stop sign as a 45 speed limit, and that will cause problems. We can extend this to implantable medical devices. The devices are implanted inside our bodies to replace a missing biological structure, or to support some like here brain stimulator, cardiac defibrillator, artificial knee, and so on and so forth. So we can use these to extend the lifetime of these IMDs, so that, because we don't want to operate on the person to replace a battery or to extend their life. We can apply this to cognitive smart cities, where we can use deep learning in a smart city to exploit data to realize new and better services for its citizens. Exploit big data with deep learning, which will help in many applications. Will help the government maintain quality infrastructure to the public in terms of roads, in terms of sidewalks, biking trails, and so on and so forth. We can improve the quality of service at the cloud or at the fog, resource optimization, where we can use machine learning to provide quality of service, to improve the quality of service to the citizen or to the users, minimizing the data and control overheads and minimize the cost in terms of, for those who are using networks, using SDN, NFV, and so on and so forth. We can use this in blockchain and use in medication, where we can find the origin, whether the medication is original or fake. In terms of improving, blockchain is used to find the originality of a certain thing. So in terms of interoperability, scalability, security, and regulatory, there are multiple applications in intelligent microsystems, as shown in this slide, where autonomous integrated smart sensing can be used, wireless sensing platforms in terms of RFID with sensors, wireless sensor networks, applied to medical, food monitoring, environmental surveillance, reconnaissance, infrastructure monitoring, as you can see in all of these applications, where the challenges are listed, in the right hand side lower here, in terms of the self-calibrated, ultra-low power, self-powered, in terms of processing, where you have to, for those who are in circuits, or where they can look at what are the sensors that could be applied here, whether be it miniature sensors or new sensors. In terms of communication, sending information, not data, ultra-low power, RF energy harvesting, and so on and so forth. We can to summarize, these are some of the design challenges. System resource dimensioning, for instance, where we can have service availability, connectivity, the workload, predicting the types of the workload and the types of is important. Service level agreement and the quality of service. If you have this application is designed for a certain region or a certain city, would that be available if you move to if the person moves to another city or another location? System virtualization and embedding, we cannot experiment with this physically. We don't have the resources, so we have to virtualize and embed these systems to design or propose new algorithms, a new system predictability, intercloud and operable and portability of the system, as I mentioned earlier. So in conclusion, we have talked here about the use of pervasive edge computing or pervasive AI, where we have a challenge, or we have a trade-off between computing and communication. And we can use it in terms of security, in terms of scalability, in terms of making some certain viable applications. We can use convolutional neural network, which is we call it learning inference, in terms of using the convolutional neural network, deep networks, and segment-based or layer-based. We use the hierarchical federated learning in order to reach accuracy in a short time for certain applications. We use the multi-agent reinforcement learning for the smart health. And we talked about some predictions or distributed inference. and potential future work and extensions for this. Thank you very much for your attention and for the invitation. And I open the floor for any questions.
All right, any questions for Professor Goizani? It's a very interesting talk, so I expect some.
Thank you very much, Professor Alam. For those who are interested, we have a lot of new ideas in these areas. Here's my email. You can contact me, or you can contact Professor Alam to coordinate any new ideas or brainstorming on some of the issues that we talked about today.
All right. Any questions from the audience? But I assume everybody understood everything that Dr. Goizani said, so there's no question.
Thank you, Dr. Alam. Thank you all for your patience and for inviting me. I'm very happy to entertain any questions in the future. As I said, I listed my email here.
Well, thanks again, Dr. Goizani, for advancing your time slot. We appreciate that very much. And we also want to thank you and give him a big hand over the cyberspace. So all right. I would also invite all the attendees to plan on attending panel 1. Panel 1 is very much related to what the government of Bangladesh is doing and what are the prospects and challenges with respect to digital Bangladesh. So I'd invite you to attend panel 1, followed by panel 2. So with that, we conclude our plenary session at this point in time. Thank you very much for attending.